start the registering. So now you might receive a message accepting the joining the session with this registration option. Now, in general, I would, particularly in the online session, and we will see eventually in the other in situ sessions, I have a little bit of a code of conduct. So if we are online and you access the session, please make sure that you turn off your mic so that we do not listen to your private conversations while we are in the course. Of course, you are free to open your mics and ask questions. I would kindly ask you to raise the digital hand so that I can make sure that I wrap up some idea. And then I let you ask your questions at any time. Please do interact, particularly when we are online, but also when we are in situ. It is very important that you participate as much as you can and open discussions on the content. So, or questions if something is not clear. So that's in the first thing of code of conduct. Then I practice diversity and inclusion in my interventions and in the way I speak. So you will see that I pay attention on equity and gender issues, but also in other cultural aspects of the discourse. If you feel that I am diminishing or not considering or being, going through comments that make you uncomfortable, please let me know that, because I'm not willing to harm anyone, but of course I I'm not acquainted with all the cultures, so I try to be respectful with this, and I kindly ask you to be respectful with your colleagues, particularly because at some point we will work together in groups, and so that is also very important, to accept diversity and include many different behaviors in our interactions. So that's the first thing. And then we will work oh yes, if you do not feel comfortable, open your mic or even your cameras for asking. Do not hesitate to write also your questions on the chat. I will take them and I will read them, etc. Also, if you do not feel comfortable speaking in English and you prefer asking in French, or if I know your language in your language, please do, and I will translate, and then we can interact smoothly in that sense. And last but not least, eventually when we will work in teams, if you do not feel comfortable working in groups, again, please let me know so that I can arrange activities that you can perform on your own if this is your preference. So that's code of conduct, and then all the material that I will be using is available online. You probably have seen in the email addresses that you declared to the school that I sent a welcome message, and in that welcome message you have the link to the course site with many material that I will introduce, and I'll let you know how to deal with all this material while we will be working together in the sessions I will teach. Attention, this concerns only the sessions that I will teach. Other professors will certainly provide other addresses or other ways of sharing their material. So just make sure that you are aware of that. At the lower part of my first slide, you see a Slack. You can also join Slack. I will eventually, while we will make a pause, I will give you the address. And what is good in Slack is that you have direct contact with me for questions or for comments, etc., or sharing something with your colleagues. So do not hesitate also to join to the Slack of the course. With this, I'm going to enter into the matter and start introducing what we are going to share in these sessions. Well, of course you are aware because I mean TV and announcements and everywhere, almost everywhere in the media, people are going around this slogan that today we are moving as a society towards a data and artificial intelligence driven society with all the implications, social implications that it has, but also with all the implications that this has with respect to the methodologies we use in our disciplines. And this course, as I said, is about this, is about understanding and having a look at the different tools that are here and how these data and artificial intelligence driven methods probably can change the way you will practice in your professional lives and address problems with different perspectives. Okay, so if we see this combination of data plus artificial intelligence that implies algorithms, today there is a methodology that implies building kind of pipelines, kind of workflows. If you have addressed industrial engineering, for example, we have different workflows with different steps that allows to use data in order to address specific problems. That in general in many domains, including in engineering and in formal sciences, okay? And so these pipelines have a general format that we will address during the sessions I will teach, which means that, of course, we need to collect and harvest data. We will see in which conditions. Then these data come in a raw status, so we have to prepare them, and again we will see that there are many techniques and implications of preparing the data. Then we have something very particular about this data plus AI trend is that now we are officially transdisciplinary. So of course you need computing science, mathematics as the basis, but that's the basis of almost all disciplines, the disciplines that you have addressed in your education, but also other disciplines that have to come together in order to solve problems, okay? So the main thing is we have very complex problems in many different domains, and the objective is to see whether these two tools, data and AI, speaking brutally and generally, can provide some alternatives in order to address these complex problems. Okay, so if they do not contribute to this, then we have to forget about them. But if they do, then we have to use them. And in order to do that in a really intelligent and performant way, we need to sit down with people of many different disciplines, of many different activities, even in our disciplines, in order to incorporate their knowledge and make sure that this combination will really help us to address these difficult problems, and that we are not in a mirage where we obtain results and we have the impression that we have solutions, but in fact these are not sound solutions. So this is very important. So we include knowledge domains. And then, of course, there is a lot of exercise in interpreting the results. You will see along the course that, in fact, we deal with numerical aspects, but that is not impressing when we have been studying engineering disciplines, because almost all our practice refers to mathematical and numerical solutions that we then interpret. But since we are adding these artificial intelligence elements into the models that we are used to handle, then we need to have specific methodologies in order to interpret the results and assess the results, as I said, to make sure that results provide solutions to our problems, and that are sound solutions, and that they are not just a matter of algorithmic possibilities of producing something that is not, in fact, a solution. And then once we interpret, then we have a solution. Let's be optimistic. So we have a solution, or a partial solution to a problem. And then we have to determine how we are going to put this solution in practice. Are we going to embed it in applications, in processes, in decision-making processes, so that a community can take advantage of these results that we produced using these new tools. And so the course is, of course, you can see that this is a quite huge thing to deal with. The idea is this could be a master even on the topic, but the objective is to provide you, as I said, the good hints and the good elements so that you can integrate this new practice in your disciplines. And then zoom into the specific challenges that you have in these disciplines. So just an overview of the lecture, and then I will really zoom into the first topic. So as I said, the general objective is to describe the principles of data science and how it can be used in your disciplines. I will teach particularly how to apply the methods and techniques coming from this data science perspective into experiments. In fact, something that it's the message that I have to pass is that we are going to experiment with data and algorithms in order to solve specific problems. And we need methods and techniques in order to do that. Methods, of course, how it's designed, but then the techniques is existing tools that you can use in order to implement these experiments and obtain results. Now, this is very important, the learning outcome. So you have to make sure that at least every session that we wrap up, make sure that it provides you with elements in order to accomplish these learning outcomes. First of all, is understand theoretically and technically the steps of the data science process. Okay, so in general, it's the 4 steps that I described previously, and for every step, the idea is that you know what are the theoretical implications of this, that you can connect them to your discipline, and that technically, which are the tools that are available out there in order to use these methodologies to solve your problems. Okay, so for every step of the pipeline that I described previously. Then regarding the tools, of course, this is a moving arena. Okay, so vendors, of course, and companies are producing a number of tools, and it is difficult to we are disoriented in all these mass of tools. And you, in your professional lives, you will be decision makers. And one of the decisions that you have to make is which are the good tools for you and your practice. And so the idea will be that I will provide you with an overview of the families of tools and which are the characteristics that you have to look for in order to decide which are the tools that best apply to your context. Okay, so this is very important that I will introduce different tools, of course, and that you make sure that you have these elements in hand. Okay, beyond the technical accidents of the tool itself that will probably change in a week or so. Then the different analytics techniques that we will address. So today, well, we all say, okay, there's artificial intelligence, and in fact, these are algorithms. These are statistics and probability-based heuristics when the problems are very difficult to address. But we also, in engineering, are completely used to apply numerical methods. Okay, almost all the first part of our education, particularly our undergraduate education, we get acquainted with numerical methods that we apply in order to address our problems. These are included in this data science pipeline, and we have to decide when and how we use them and instead why and when are artificial intelligence algorithms useful as complement to numerical methods that we've been studying for years now, since you are now in master. So again, it is very important that not to use heuristics because they are trendy, but really understand where they can really provide and contribute as complementary visions of the way we practice engineering since ages. And then, of course, everything is done to make decisions about processes, make decisions about actions on smart cities, for example, make decisions on how we deal with energy in the best manner possible, which are the types of energies that we are going to apply within a certain urban space, for example, in order to reduce CO2 or whatever. So these are the type of decision-making problems that we have to address, and then see how we can provide decisions that are backed up by mathematical models. Okay, we do not decide because we imagine or empirically because we think this is good or not, but we support our decisions with concrete arguments that support this. And this is a very important, maybe this is the most interesting aspect that provides data science today. It is that we want to reduce as much as possible empirical decision making. Okay, and that we have, and we keep track of the way we reason in order to provide solutions to problems. Okay, and this is tracked, and this implies a lot of data, and so there are tools that can help us support this in an automatic manner. So the course is theory as today. So today I apologize in advance. I will talk a lot, but maybe this will be the only day that this will happen, because the idea of this course is that you put hands into the matter, okay? And so we will have, of course, the classic introduction of theory and terms and concepts. the idea is that you acquire the right vocabulary when you talk about data science, and also that you know when someone comes up with a concept, that you know how this concept is related to your discipline. So that's the theoretical part. Then we will, of course, rely in your statistics, probability, numerical methods knowledge, in order to build data-driven solutions. And of course, I will introduce some aspects of artificial intelligence in a very general manner, because we don't have a lot of time, but that can give you the entry points to use these tools in your disciplines. And so we are doing the introduction. We will see how to design experiments, and we will see that there is a problem of scale. If you are not data science specialists, but you are other discipline specialists, you still have to play a little bit with the design of the experiment, with portions of data, in order to estimate that a data-driven solution can help you to address your problems. And this happens in an in-house environment. And when I say in-house, is you can use either your personal machine, or you can use existing supports available on the cloud, or from your IT department, in order to perform these estimations and see which are the general elements of this design. And then once you think that a data science can probably provide insight on your problems, then you will go into a different scale, where you will deal with more data, where you will need also much more computing resources in order to perform a more realistic experimental tests. And there you need IT in order to support this medium level experimentation. And once you have you are sure that this can work, then you will really go to scale. And going to scale implies really working with an IT department with the data engineering expertise, so that they can put in practice the experiments, but the whole process must be controlled by you, for example, energy or smart cities experts. So you have to make sure that you know what are the challenges in the different scales, and what is your role in these challenges. And this will happen in the second part of the content, when we will discuss about designing experiments. And then we will go, and here we will have started dealing with some hands-on and theory, and then the rest of the content will address examples of problems using different techniques, including, as I said, artificial intelligence algorithms, in order to address specific problems. These will be hands-on, and this will happen in situ according to the way your programs will be organized, in order to have this practical experience. So this is the overview of the content. So descriptive statistics, statistical inference, and unsupervised learning will be the three parts of the course that will happen in the lab and in situ. So this is a general overview. Of course, you have guessed that today you received information about the course. So I want to make sure with the Scholarity that this is the way we are going to, organize in terms of dates. but well, today we have a magistral theory lecture 1 with 2 sessions. Then we will have probably another one the 25th. So I think that it's next week. And then we will divide the group according to the programs and the rest of your schedules into 3 sessions, where we will go to the lab and play with data science problems. Then, of course, about the grading of the course, every professor intervening in the course decides whether she or he will provide questions in the final exam. And the value of the questions are pro rata with respect to the number of hours that we teach the general course, okay? So for my part, I will propose a wrap-up activity that will that is worth 40% of my grade. Okay, so little part of the general grade. And then during the final exam, the questions that I will propose will complete the 60% remaining, and so that you can have a grade of the part that I am teaching. Okay, attention, I insist, because I mean, sometimes, and particularly if you belong to the French system, this can be weird, but okay, for my part, for the number of hours that I will teach, you will have a grade that will be then pondered with the rest of the grades of the other professors, and these are the percentages of what of the different work that you have to do in order to grade a grade. And again, for those that are not acquainted with the French system, the grades, my grades will be noted over 20 points, okay? So I'm reachable online all the time. I mean, in situ, it's difficult because you are in Grenoble and I am in Lyon, but do not hesitate to contact me by mail or eventually through Slack, and I will answer almost immediately. Or immediately with respect to the time zone where I am. Today I'm in Sao Paulo, and this is why I'm not in situ today. Okay, just before we really start, I want to show you the organization of the site. This is important because you have all the material there. Okay, so I'm going to stop a little bit the slides, and I'm going to open. So let me see. I'm going to write the. You have the address. You can click on it on the chat. So so the site looks like this. You have a general context and motivation of why I am teaching what I'm teaching. Then you have the objective with the learning outcomes that I have discussed some minutes ago. Then you have the content. And in the content, you have, well, this is an old YouTube session. Today, I'm recording, so I will update it with the session that we are recording just now. So you have every time the content of the slides. And then if the session is online, I record it and you have the video there. And so for almost all the topics, you will have the slides. For the time being, I did some modifications. You will see during the session why, because other advances in artificial intelligence, and particularly ChatGPT, is here. And so I updated the content of the course in order to position the content with respect to these new tools. And so it will change a little bit, but the updated content will be here available for you. Then, as I said, there is a lot of hands-on aspects to consider. So I will not go through the details because we will do step by step, but in the hands-on section, you have the descriptions of all the hands-on, the technical aspects, etc., that we will address during the lab. And the good thing about the lab is that after, I think, 3 or 4 years that I have taught the lab online, we will meet in situ, so it will be easier to explain how to use all these in the different exercises that we will address in the lab. Then, of course, it is always important to have like general references of the content. Again, I will update a little bit here, but it is important that, of course, my slides are good for me, but do not hesitate to take notes, and I will provide some reading references so that everything that is said here can be, you can refer to in a text eventually, so that you do not lose yourselves in this, in my speech, okay? So, and then there is more consequent bibliography. There are some cheat sheets and things that we will use during the different sessions. So I will alert you on where to have a look with respect to the bibliography. And then knowledge control. Of course, we will have these several hours sessions, and we will have the hands-on with different techniques, etc. And the problem is that then some months will go by and then the exam will come back. Okay, so you will probably forget some things that have been said. And what I have prepared is a set of questions. It's not a questionnaire, okay? It's just the questions that you have to make sure that you can answer in order to be sure that the learning outcomes that I state in at the beginning of the course are there, and that you can easily answer to these questions, and this help you prepare for the exam. Okay, so this is the general idea. Of course, again, if you have comments, etc., then do not hesitate. And lecturers, there are many lecturers because this course is given in different institutions. In the case of you, I am here, but as I said, you can contact me whenever you need. Okay, so do I have questions or comments until now before I go back to and start the real serious matter? So again, at home or eventually when you will wrap up all that has been said, if you have questions on on these administrative aspects, do not hesitate to contact. Okay, so I'm going to start with the real content. And in order to do so, I'm going to start with this slogan that represents, I would say, that the general spirit of the course. Some years ago now, like more than 10 years, I think now, if we consider big data, Pythian said that the main trend that we were expecting to emerge like 10 years ago is that data is everything and everything is data. Meaning that with the evolution of technology, being able to almost observe and digitalize every phenomena happening in reality, this digitalization implied producing data-driven representations of these phenomena that we could archive and that we could process through different methods. And this digitalization of reality made it possible to reason about this phenomena in a digital way. And when we say digital way, using computing solutions. And data is everything there. We can have a little bit of a problem, but the idea is that if we have the data, the necessary data and the representative data of the phenomena we observe, we can expect to model, understand, predict, and eventually reproduce almost every phenomenon happening in reality. Okay, so this was the slogan that drove, of course, science, but that drove technology and that drove industry in order to go through this data revolution. Okay. And this was possible because some years before, there was the big data trend, saying that it was possible to turn reality phenomena into data thanks to this big data trend. Okay, so suddenly we realized that a lot of data about many events happening in reality was gathered and has been gathered for a while. And that thanks to, if we could process and exploit these bunches of information, we could reproduce some reality phenomena, some happenings within phenomena, and that was big data. And then we'll see in a minute, there would be technology, etc., accompanying this trend. And at some point, this was stabilized. Big data was no longer a buzzword, but then we moved forward into the slogan, data is everything and everything is data. And then we moved to a more ambitious objective, which was datification. The notion of datification, which is should be now part of your vocabulary, is that since we were able to digitalize every phenomenon of the reality, so we were datifying reality and phenomena. And this, I mean, this had happened before in small scale, and this was also accessible for scientific communities, essentially. But the thing was that now this datification was democratized, and every citizen of the world with the necessary tools could exploit these elements. And since we are talking about scale before, where we could put sensors in some places and have observed some phenomena, but now this is everywhere, okay? And even the most stupid things happening in the world were datified, and people can reason and about this, okay? So this is datification. And then why do we need this? Well, because in fact we wanted, I mean, the glorious perspective of datification was that we need to have to promote analytical knowledge. So the idea is that together, once we have the data, applying algorithms and mathematical models, etc., we could produce well-supported, evidence-supported analytical knowledge. Okay, what happened before? If we wanted to observe a phenomenon, in fact, since we didn't have enough technological resources, the observations were limited, and we had samples of what was happening within a phenomenon. But now, since we are changing scale and since we are constantly observing phenomena, this means that now we have representative observations, amounts of observations of such phenomena, and it is possible to have a more complete, probably, analytical knowledge about these phenomena. Okay, so that's the first glorious thing to consider about datification. And the other aspect is that our decisions will be evidence-based. Okay, so it is no longer acceptable to have important decisions made without evidence. Every decision has an associated evidence, and this doesn't happen again for just companies or for just scientific communities, but any person in the world can access to this. Okay, so that's the project, if you want to see it like that, of datification. And this project has been instantiated in the different communities and the different sciences, and it has its interpretation. Of course, in this course, we are going to see the interpretation of how smart grids, smart cities, and smart environments have instantiated this notion, and how is it possible to use it. And because of this, then many sciences evolved, okay? And this is the other concept that it's important to bear in mind, is there are data-centric or data-driven sciences. The idea is that if your science, or if some problems in your science can be solved through experimental processes, data-driven experimental processes, then your science will become an experimental data-driven science, and you need to develop the right methodology in order to address or revisit the problems you have been addressing in your science through this eye, okay, through this datification eye. Examples of these, well, now these are just a few of them, but now we have plenty of them. For example, in social sciences, that observe human behavior, for example, or economy, etc. There is a move and a trend trying to use this datification idea and revisit their methodology. There are other sciences that appeared due to this. For example, the network science. Some mathematicians in different communities realized that it is possible to represent phenomena as networks. And if you manage to find the right network type that represents the phenomenon, you can address complex problems by analyzing the network. Example of this is in biology. For example, the first H1N1 pandemic before the COVID was addressed with this network science. In fact, it emerged in order to deal with terrorism, and the DARPA in the US supported a center of network science where they solved and they identified and they tracked so-called terrorists, or that they considered terrorists, in order to, they tracked them and they found where they were, okay? So this is network science. And then, of course, with social networks, it became also quite popular. Then in digital humanities, again, there are some very interesting projects derived from this datification perspective. Example of this, for example, in the opus of Bach, there are some compositions that musicologists are not sure whether they were authored by Bach or not. This is an open problem in musicology, and so with data-driven datification-based solutions, they are addressing this. And then you have probably or certainly seen that now it is popular to reproduce the way Van Gogh or Leonardo da Vinci, etc., produce their art and have versions or new opus of their production based on the patterns they used in order to produce art. Of course, here I'm not going to discuss about ethical and epistemological issues, but the only fact is that this is happening, and this is because of this datification movement. And there are other computational sciences that also deal with this and that have become very popular. Now, the backbone of all this is, of course, data, as we have said. And how does it happen? So, well, the idea is that you have data regarding different phenomena, and then you are going to conduct experiments on top of this data. These experiments will be driven by hypotheses, if you already have a hypothesis, or will help you derive hypotheses about some problem, okay? And a very, very important thing to consider is that the results of these experiments produce models, simulations, and understanding that are valid to some extent. There is no longer a notion, and this is really important, there is no longer a notion of complete, sound, and definitive result, experimental result. The results are valid to some extent, and the idea is that this some extent can be measurable, okay? So results are accompanied with scores that determine the degree of validity of such results, okay? We all, for example, use Google as search engine or similar search engines. And normally, okay, we write our keywords and then we have results. In fact, the results and the order that in which they are provided, and the reason why some link is contained in the result and not other, are accompanied by precision and recall scores that are not explicitly given by search engines, but that we should bear in mind. Okay, these set of results are valid to some extent with respect to a precision and recall scores that determine to which extent these results represent a solution to our keyword query. Okay. So the problem is that, I mean, many people, including myself, I sometimes tend to forget this, but this is a partial result, and it also depends on the location where I am. Okay, so as you remember, for example, launching a query in Google, for example, here in Brazil or in Europe, provides different results because the portions of the data are separated. Okay, so the result is valid to some precision and recall, and with respect to the data contained, crawled, and contained in the servers of specific regions. Okay. So as this happens in very simple tasks that we perform for searching information, this also happens when we design experiments using data-driven strategies, okay, and algorithmic strategies. They are valid with respect to a set of scores and a set of references that give the perimeter of their validity. And the good news is that this perimeter is measurable. And why is it important? Because therefore we can provide evidence-based and non-empirical decision-making strategies, okay? And we can more or less measure all this. Now, how do we do this? Okay, this is nice. And so me and you and everyone who wants to use, I'm just checking the time so that I do not go further forever. So how do we do this? Well, materially, this implies, of course, developing methodologies that weave many different aspects. They weave data management. At the end of the day, we have the data harvested through different techniques. There can be technological techniques like putting sensors in places, like tracking the use of a credit card for online purchases, I don't know, tracking the operations and the behavior of some user when she or he uses an application, things like that. And all these data are gathered and they should be managed. The first problem is, where are we going to store them? If we are talking about some teras today, we can easily have NAS support in our living rooms with terabytes capacity or a computer, but then when this grows, where are we going to store them, right? And then how are we going to organize the data such that we can retrieve them easily and on time, and that we do not forget what do we have? Okay.
I didn't catch that. Could you try again?
No, Siri. So it's Siri.
Hi, Genevieve.
Sorry, I have to turn off my Siri. Yes. Okay, so if you probably, and I believe that this happens to all of us, we gather photos or we gather PDFs that we consider interesting, but the PDFs, the name of the files are not representative, and at some point we find out that we have bunches of images and PDFs, etc., and we do not remember what are they and why we consider them interesting. So again, this happens at our scale. If this happens in a really big scale, we have to figure out some ways in ordering and the data and classify, indexing it such that when someone needs some data, it will be possible to know that we have data about what we are looking for, that when we retrieve the data, we are using all the data available that we gathered, and then use the computing resources, particularly storage resources, in the best way possible, so that we do not spare the resources like as if we were millionaires, okay? Because this also costs money. So that's data management. Then we have to process the data, and the way we process the data using computers is through algorithms. So normally the algorithms that we use in order to process the data are considered greedy. Greedy in terms of how much CPU, main memory, and main memory essentially they need in order to be executed. Okay, you remember that we are rich on storage in general, but we are not that rich in main memory independently of the architecture we are talking about. Okay, so many algorithms need the data to be uploaded in main memory so that they can work, including, for example, numerical algorithms, okay? And so if we are talking about bunches of data, we have to make sure that these greedy algorithms can use all the data despite of their volume. So we combine greedy algorithms, and this can be estimated. You have probably learned this in the basic courses of programming or algorithmic thinking. We can estimate the amount of memory and CPU that an algorithm needs, and whether and the complexity with respect to a complexity index that can refer to CPU and to main memory. So all the algorithms are have this associated profile, so it is possible to determine how we are going to use them despite of the volume of data and despite the resources, computing resources that we are available in order to process the data. Now, since we are talking about scale, okay, we like working in-house, but we would like also to move to other scales. When we move to other scales, and particularly when we want to execute greedy algorithms in reasonable time, we need to change programming models, okay? Normally what we learn in undergraduate studies is the sequential programming model. But the sequential programming model, for some greedy algorithms, we cannot expect the solution to come in reasonable time. And so other programming models open the possibility of having results in reasonable time, okay? So we have to combine this. And then, okay, this is design, right? We know where to put the data, we know how to process them, we know how to implement the algorithms in the right programming model so that it can provide results in reasonable time. And then where are we going to run the experiment? It's like choosing our lab, okay? In which lab am I going to perform this experiment? And this calls for computer architectures. So today, if you are online game players, you know that many games require a very high video quality, right? And so there are hardware devices that ensure this quality, and that we see the scenes smoothly, okay? That we do not see the per people and the action like this, but it runs. And so some popular hardware is GPUs, okay? So GPUs is another type of processing architecture. So the idea is how, and there are many, okay? So which is the right target architecture, computer architecture, that can be adapted to the kind of experiment that someone wants to run. Okay, so this is the big challenges that come together in a data-driven experimental solution. Questions until here? I'm going to survey the chat, because I said that you can ask questions on the chat, but I'm not having a look at the chat. Oh yes, I have one. Oh no, that was me. No questions? Everything is a lot, but fine until now? Okay, thank you, Diego. Right, so once we have said that, okay, we are going to combine many different tools, etc., theoretical and practical tools. So what do we do with this? For doing what exactly? Well, in fact, all the experiments that we are going to run with the data and the algorithms, etc., must be intended to answer questions. And in the data science jargon, these questions are called research questions, okay? And these questions can be classified in essentially 4 types of families of questions, okay? And for each family, it is possible to identify possible algorithmic tools that can be used in order to answer them. And there is an axis here that is missing, depending on the quality of the data and the kind of characteristics of the data that we have available, okay? But I will come back to that in some minutes. We can have questions about some phenomenon. Remember that we are dealing with phenomena, okay? Essentially complex phenomena. Okay? And so we want to understand what happened, okay? We have a lot of observations and we want to answer to the question, what happened in fact? And so for that, we already have, and we are already used to such problems and to such solutions. We already have statistics. Okay, normally when we use statistics is to answer questions of, of questions of the type, what happened? And this is because we are looking for insights, okay? Just understanding what's happening. And despite the complexity of the possible implications of the question, the solution is elegant. We need descriptive analytics to perform this. So by knowing how to handle and how to use in a very strategic manner descriptive statistics, we can answer already this type of questions. Okay, no need to nothing. Then what about greediness, and what about different target architectures, and what about this complexity? Okay, because some of the when data become large, computing the values, the indices of that defined by descriptive statistics can cost a lot of computing resources. Okay, so if you have bunches of matricial data, for example, computing the maximum of some attribute can be costly. Okay, and so the idea is to figure out how to perform this operation in reasonable time, despite the fact that we have to process a lot of data to compute this value. Okay. So this is where the data come from. And another problem that is very important and for which all mathematical models are very sensitive is the quality of data. For example, you all know that if you compute, for example, the average of some values, numerical values, but that there are a lot of missing values or values that are kind of outliers, your average will be not representative. Okay, so and this is because this implies that we need first to clean and have a smooth distribution of the values so that when we compute average, the average is representative with respect to the elements of the sample. And this happens with different indices, okay? Yet, when we are talking about data out of the datification trend that come from sensors that sometimes work and others not, that they are transmitted and within the transmission they are corrupted, that people are entering the data and they are incomplete or they are nonsense, etc. All this garbage that is included in the data collections has an implication on the quality of the answers that we will have if we use descriptive statistics, okay? So we need to consider that this kind of method is adaptable when with respect to the quality of the data we have. And you would say, well, we can clean the data, but sometimes if we do not have or we are not surrounded by the right context or people that know the context, it is very difficult to decide whether, for example, an outlier is a real outlier or not. Okay, so and if we impute the outliers as such and we get rid of them, we might be losing important information and maybe information that will have an impact on the way we will perceive what happened. Okay, so when it is not possible to clean the data as such, we can use other methods, and particularly coming from machine learning and artificial intelligence disciplines that are less, they are not at all sensitive, but they are less sensitive with respect to the quality of the data. Okay. So this is what happened, and you already see that there are some elements that makes it important to apply the famous data science methodology in order to make sure that we obtain representative results. Then another family of questions that we can ask is, why did it happen? Okay, I put on weight during pandemics, for example. Why did it happen? Because I was depressed, because I was at home eating everything, or because the COVID produced altered my metabolism and so I put on weight, or because I was sitting on the couch and I didn't do sport, okay? Which are, why did it happen, okay? Or maybe because of all of this. And so this is diagnosis analytics. It can, it is possible to use some statistical or probabilistic methods, and also machine learning and artificial intelligence in general. Machine learning is part of artificial intelligence, but they have a kind of special rack on the classification. So that's this other type of questions. And then while we start moving, we are no longer wanting to have hindsight of the data, but we want to have insight of the phenomenon. Okay. Then once we with these two, if we manage to answer these two type of questions in from some data collected observing the phenomena, we start having a good understanding of this phenomenon. Okay, so we know what phenomenon appeared, the phenomenon that appeared, and we know, or we have elements to know why did it happen. Okay, and if we gathered enough insight and insight about the phenomenon, we can start moving into answering what will happen. Okay, out of the events that happen within a phenomenon, I can eventually, understanding them, I can eventually predict whether these events will happen in the future. Okay. Example of this, I gather a lot of physiological metrics about people. And I, with respect to these physiological metrics, I see that some of them acquire or not a disease. And I have a lot of that. Okay. So I understand which are the right values and how these values are connected. So what happened? They acquired a disease, giving a set of physiological values. I can eventually know why did it happen, why a person giving a set of physiological values contracted a disease. And then once I know this, I have this knowledge, given a set of physiological measures, I can eventually say whether a person will contract the disease or not, out of the experience and out of the observations and the conclusions I did while answering this type of questions. Okay. Now here, well, you are engineering educated people, so you know that prediction can happen with statistical inference, that you can use different families of regressions, which are mathematical models to solve prediction problems. But these models, as I said before, are very sensitive on the relation, for example, of the variables. For example, in regression, the target attribute must be linearly independent of the others. Okay, they have to, the values of the different values of an observation must respect some, they have to be normalized, okay, or some distribution or specific distribution so that I can apply some regression function, okay? So these strict rules about the conditions in which I can apply these methods do not appear, as I said, in some other heuristics coming from machine learning and artificial intelligence that can help me predict without these strict restrictions, okay? So how am I going to answer these predictive problems? Well, it depends on the input data that I have. Or I can combine, of course. Okay? Okay, so now I am able to predict, and what comes next? Well, I can, so this is foresight. And then once I know a lot of the characteristics of the phenomenon, I have a quite good understanding of it. I can even predict with some precision extent some outputs. Then I can eventually know and determine how can I make it happen. Reproducibility. Okay, and why do I want to reproduce? Because I would like to optimize. For example, I have participated in a project dealing with makeup. And the idea is that makeup is essentially powders, okay? And you have to make sure that the powders are compact enough and in some form such that when they transport it, it doesn't break easily. Or when you touch it with put it, that you do not break it, okay? The tests are done not only in predicting whether these pieces of powder, compacted powder, will break or not, but they want to reproduce the conditions in which the powder breaks, okay, such that they can, while transporting, or such that when they package it, they can avoid this problem, okay? So how can I make it happen? How can I break it and see which are the conditions that come into the matter such that it breaks, and so that I can eventually control these conditions, okay? And again, why? Because I want to optimize the size of the package, the form of the package, the conditions in which it will be transported, etc. Okay. So this again can happen with applying interesting methods in artificial intelligence. Okay, but again, out of this, okay, guiding element about doing data-driven experiments is the type of question. Why? Because the type of question will determine the type of method I will use in order to answer it, okay? From one side, and on the other side, it will, the method I will use will be also determined by the quality of the data I have gathered in order to answer this question, okay? So when someone comes and say, I have this data and I have this question, is it possible for me to use this data in order to answer my question? These are the kinds of elements that you have to make sure that exist. The quality of the data, the type of question, and the relation between the constraints associated to the data with the type of question, and then determine whether a method exists, an algorithm exists, or a mathematical model exists that can help you answer the question. Okay. So these are the type of exercises that someone wanting to use data science to address his or her problems will ask. So now you, after the course, you have to be able to do that. Someone comes with your data, or you yourself collect some data, you have some questions, and then you determine whether using this data you can answer such questions given a specific model, or whether you need to complete the data, process the data, etc. beforehand, such that it will be possible for this to happen. So that's the objective of us in this community. So let me see what time is it. So that, okay. So we have to 1 hour, more or less. Okay. Now I'm going to go a little bit fast on this. These are examples of applications where this kind of reasoning of problem solving methodology can be applied, of course, in business networks, retail recommendations. So you are people of your time, and you might use retail applications to buy things, no, or access to content. So these recommendations, for example, in retail, those that bought this book also bought this book. Okay, so this kind of recommendations for reading, for films, etc., are addressed with these type of methods. The way social networks work, okay, the kind of suggestions that it provides you for contacting other people, for accessing to content from specific pages, the way it presents the content in timelines. All this is done with respect to profiling and, of course, using this type of methods. Then everything that is wearable, used to monitor, for example, your physiology, your physical status, etc., and then provide you with recommendations on strategies in order to be better, breathe better, etc., are also examples of applications based on data science solutions. Everything that concerns machines management and maintenance. For example, I used to have a project in China, and they wanted to determine, they had a flow shop, okay, with different machines, and there were robots putting the input, the primary goods, into the machines, and then the machines processed it, and then again and again until a product was produced. And the question was to predict the period of time in which a machine will break down. Because if a machine breaks down, then the whole flow shop process is damaged, and you do not respond to some timelines. No? So, for example, there, the idea was to observe, etc., and determine, and particularly while the machines are electronic, they have electronic devices that provide signals, and so the idea was to observe the signals in order to determine during which period of time there was a risk for a machine to break down. Then other things like emails, for example, classifying emails, determining whether an email is a spam or not, etc. So these kind of applications are possible clients of data-driven solutions. For example, again, we used to have a project on managing crowds in urban spaces, and the idea was to determine whether there would be a problem of, when the crowd becomes crazy and people are crushed because people start moving because of a disaster or an alarm, etc. So the idea was to determine whether within a specific path, people could be dying because of the flow of the crowd coming on top, and there would be bottlenecks in the urban spaces. So these kind of things are clients of data-driven solutions. Okay, so now, okay, we have the clients, we have the questions, we have some elements, some hints about the way data works, and then how do we start touching concrete? Well, there are three elements in order to drive data-driven solutions using a data science methodology. Of course, there is data, and this goes back to the promise of the title of my part in the ICT course. It's big data, okay? So what's big data, and how does the big data represent in this experimental methodology? So that's one thing. And the other thing is that big data, whatever it is, general data, can work and can provide some good to solve problems, is because of two things. Because we are able to design experimental settings, okay? And the experimental settings are related to our choice of a computing environment that will run our experiments. Again, I know that I do not have in this course a computing science audience, so the interface here is how are you going to interact with an IT department in order to express your computing requirements such that they can prepare the right experimental setting with the right hardware, software, etc., that can help you run your experiment at different scales. Right? So that's first thing. Then second thing is computation. Okay, you have the data, but you have to process it. And I have presented all the types of questions and possible families of methods. So the question is, which is the right mathematical model or algorithmic model that will help me answer my question given some data? And how am I going to implement it? Which are the requirements such that I can use it? Okay, so it's like a hammer, or okay, I have the hammer, but how do I use it? Can I use it for my problem? And then how do I prepare myself in order to hammer the data? Okay, so for every model, there are conditions. And so you have to be aware of the conditions. Again, you are not a computing science audience, so you are not going to program, or yes, but very little, but we are not going to study how to parallelize an algorithm such that it can run on a GPU. That's not the objective. If you were a computing science audience, then we would have to address it. Yet you have to declare your requirements such that someone, if the algorithm is not already implemented, how can someone implement this for you so that you can use it, okay? And that it corresponds to what you need. Okay, so in terms of professional profiles, this is done by a data scientist. Okay, so of course you are there and you have your mathematical education that can state the problem, can see the data, and can express the requirements. But then data scientists will be there in order to state all this in a way that it can eventually go through an experiment. Okay, so this would be a data scientist. And then how do you put it on the run? This is, and who prepares the right environment? This is a data engineer. Okay. In between, you can, and then what happens with the data? Well, there is a data manager. There are also other profiles like a data steward. Do you have the right, or do you have enough data, representative data, or data coming from the right source in order to run your experiment? This is a data steward who will say this in an organization. And when the data manager is the one that is going to put the data on disks, decide whether it should be fragmented or not, distributed or not, ensure availability, duplicate some data if they are critical, etc. Okay, so this is here. And we in this course, we are like here, profiting from all these people to design our solutions, to state our problems and design our solutions in a short scale but formal manner. Okay. Okay, so we are going to begin with data because the course at the end of the day is called Big Data. So the buzzword, as I said at the beginning, has happened long time ago. And now what remains about the word is a set of properties that we can associate to data collections, and that which that will determine the way we are going to process them, okay, and use them. So you have your bunch of data, and of the big data buzzword suggested big, and big suggests size, right? So there are many properties associated to the data, but the first one that we can discuss is volume, okay? Since we are relating it with the big adjective. Now, volume has been an issue for a long time, for all the history, along all the history of computing, okay? Yet you have to know that humanity managed to go to the moon without storage and with very few volume of data, okay? 64K to go to the moon at the beginning, okay? So, but at that time, 64K was a lot, okay? And then while the history has been moving, we never stop, okay? I was telling you that I can have sitting in my living room a NAS. A NAS is a rack of disks of storage with several terabytes of data at home, okay? And we went to the moon with 64K. Do you imagine? It's incredible, okay? So the question is how volume has an impact on the way I will analyze the data with algorithms. And there, things change because I need to have the right computing resources such that huge volumes of data can be processed using greedy algorithms, okay? Algorithms needing a lot of computing resources. That's the big question. Do I have enough main memory, storage, and computing cycles available to process a specific volume of data? If I do, then I can move forward. If I don't, I have to make a decision whether I can look for a solution that provides me these conditions in order to process my data. The second thing about volume is that at the end of the day, this data must lie in hard disks. And the question is whether I have enough storage support to store them and to ensure that they will persist along a certain period of time, despite the evolution of storage technology. You are probably very young, but CDs, for example, were a great thing, okay? Because they had a lot of much more storage space than other supports. The problem is that CDs have a short lifespan to store the data. They are erased. If you want your data to persist for many, many years across centuries, then you need to make sure that what was lying on CD, which was the trend of the moment, how can I evolve to other storage supports so that I can ensure durability of my storage, okay? So there, volume has an implication. Just for the gossip, today there are solutions based on biology, based on crystal, in order to ensure be able to store a lot of data in short spaces, because it's also another problem. And if you are if you're addressing energetic problems, for example, the problem of having a lot of disks is that they consume a lot of energy and that they produce their CO2 footprint is enormous. So the idea is, since I have volume, how do I manage to have the right technology and reduce, for example, energy and CO2 footprint, and still have a lot of data. So that's volume. And you, in your companies or in your practice, in your professional practice, you have to determine more or less to which extent you will have some specific volume, and make sure that in your companies, in your organizations, you have enough storage support to maintain this, and for how long, and in which conditions. Okay. So this is where volume has an impact. Second property. Remember that these are properties derived from big data, because we are kind of erasing the buzzword and seeing what are the implications, what is behind this buzzword definition. Okay. The other problem is velocity. Of course, at some point in history, data came like in batches, no? Puff, and then puff, and then puff, but they are in discrete periods of time. Technology has evolved now, and it is possible to have real-time production of data, particularly if I'm telling you that I am observing reality and phenomena within reality, and I have these sensors observing this. Well, the data is being produced at high pace, maybe not in real time, because these devices are also discrete, but at very high pace. Okay, so this is called velocity, the pace at which data is produced. If the pace is very high, we have continuous production of data. And this is represented by the property velocity. So when someone comes with the data, it's not enough to say, I have this bunch of data. You have to, and even if you do not do computing science, you have to determine and know at which pace new data of this type are produced. Once in a month, once in a year, once in a millisecond. Okay? Because these will have implications on the way you store it, you process it, and you consume it. You have to, if a lot of data is coming, you have to be able to consume at that pace. Okay? Let's consider our applications, our traffic applications. Our traffic applications are not continuous, because our phones, our devices in the car have restricted resources. Okay, so at some point they are updated, but not continuously. Okay, so, and this is not dramatic, because we can manage still to go from one place to another thanks to the application. Okay, but anyway, this is velocity. Okay, volume, velocity. Now, when we talk about data coming from different places, right? Data coming from the traffic, data coming from my phone tracking where I am, data coming from my profile, etc. And particularly when I use different hardware, many times hardware have proprietary data representations, and different hardware, different proprietary representations. So this means that I have a huge variety of data, maybe representing the same observations, but in different formats, or described with different attributes, different variables. Okay, so if I, for example, use an iWatch to follow my my physiology, the type of attributes that it will use will be different if than if I use a Fitbit solution. They have other names, and this variety is important, because I have to consolidate all these informations and then eventually analyze it. Okay, so the problem with variety is not variety itself. We have been dealing with heterogeneous data for ages. The problem are volume and velocity. In classic solutions, you have, like in maths, no, a pivot model. So data came in different formats, they were processed and they were represented in a pivot model, and then they were analyzed. The problem is that now velocity, the pace, can be very high, and the volume very high too. And when you process data, you have a cost, okay, particularly in time. It takes time to process the data. And I have to maybe have critical decisions at the end of the spectrum. So I cannot afford anymore transforming the data, all the data. Okay? And so variety poses the challenge of dealing with data heterogeneity without or with small transformation processes. Okay? How do I deal with all this variety? So this is the third. I'm presenting the 5 main. In a minute, I will tell you that the V's are enormous and that the VMIS model have evolved a lot, and there are many V's, but these are the more or less the most important ones, at least for the things that we are going to do. Then comes veracity. You have probably studied foundations of databases, the relational model. And if you have not, do not worry, in this kind of strategy, there is a notion of data consistency. Okay, data must be consistent, meaning that they different data representing the same observation have the same structure and respect certain intervals of values, okay, essentially. And if they do not respect this, we consider that they are inconsistent, and normally in this kind of classic solutions, you do not accept a new data coming that does not respect these restrictions to adhere a data collection, such that you are sure that every time you maintain a consistent collection. Yet, when you observe reality, you can have different observations of the same subject of observation. And all are true, even if they differ. For example, if you want to install a set of sensors in order to determine the temperature of a room, in order to decide whether automatically you can launch the climate, the air conditioned, to ensure a level of comfort. No? If you distribute the sensors across the room, the sensors, well, you all know that at the top, it might be hotter than down, or near the window, it will be hotter than near the door, I don't know, okay? So your sensors will produce different readings about the temperature of the same object of study, which is the room. Are they wrong? No. They all represent the temperature of the room. And so you have to deal with these different readings and have some strategy in order to deal with these different readings and still be able to determine which is the temperature of the room and make decisions out of this. Okay. So you have to accept different levels of veracity in your data. So you are going to move from very strict ways of managing data collections through very open and flexible ways of managing data consistency in data collections. And this is a very big problem because this addresses the problem of data quality. Are different readings do different readings imply good or bad quality? It depends. Okay, and all the challenge is to determine this. Right? And finally, we come to value. For many years, and at least when we study in academia and formal studies, we barely talk about economic value of the things that we do. Okay? How much does it cost to send an email? How much does it cost us to have this Zoom session across borders, across the sea? Okay. This in an economic perspective, we do not consider. We are kind of think ideally of the problem without this external restriction. Yet, while data has acquired specific values on these properties, and that they require particular resources, value has come into the matter because people that maintain, produce, analyze these data collections invest in infrastructure in order to deal with this. And this investment, economical investment, has an impact on the cost, the economic cost of the data. Okay. And some years ago, for the first time, we started to determine which is the value, economic value of dealing with data with these levels of different properties. Okay, how much does it cost to deal with variety? How much does it cost to deal with different levels of veracity? How much does it cost to deal with specific bytes, terabytes or whatever bytes of volume, and again of collecting data and processing data continuously? An example is if you are stream consumers, songs, music consumers, this is an example of economic value associated with data. You can access, for example, well, in some solutions, you can have access to a song and pay some cents. No? And you only, instead of buying a complete album, you buy a song and you have it available digitally. If you have streams, then you can have for, I don't know, $12 access, global access and continuous access to music material and other types of sound material online or connected or disconnected manner without publicity. Otherwise, you should be connected and you have to accept some publicity. This is because there is an economic model associated to the management of the data, in this case, music or other kinds of content. Okay, so when we design data-driven solutions, we have to think about economic value and determine which is the cost of economic value of a specific experiment, which is somehow new aspect that was introduced in this big data trend. Now, today, there are other important non-economic values associated to the management of data with these properties, okay? For example, energy. For example, CO2. For example, other horizontal properties like privacy, like giving control to data to their owners, etc. Okay, so these elements can be integrated into the value, sustainability, for example. And this kind of non-economic characteristics or that can determine the value can be considered and have a model on the way we maintain, produce, analyze, etc. data and develop experiments. So if you want to say, I know about big data, you have to know the properties and what do they represent. Okay, and with that, you have a classic knowledge of big data. Then the data, the references, the numerical references of metrics of these properties have evolved along from the moment at which big data was a trend until now. Okay, and this doesn't stop. Okay, we continue producing a lot of content, etc., with velocity, with and so some people have started to reason about the way we measure these properties in numerical references, and particularly with respect to volume. There are new trends trying to define new ways of measuring volume and considering what is the smallest piece of unit of volume that we can expect to deal naturally. Okay, because what you have to know is that when the big data buzzword started, the definition was that everything that goes beyond existing technology has to be considered as big data. Otherwise, you are pooling resources, but it's not big data. Okay. And then at some point, technology evolved a lot, and now we are really able to deal with really huge amounts of data. But this means that the lowest piece or unit of data that a normal person with normal access to resources deals with is enormous. And so new units have started to emerge. For example, talking about big scale, a trend in the IEEE analyzing this problem defined that the shortest unit of data that someone would deal with was 1,000 yottabytes. I will give you the scales in a minute, and this would be called a brontobyte. And then the next is a mil brontobytes, 1,000 brontobytes would be a geobyte, and etc. And which means that any classic architecture should be able to deal with this amount of volume of data for storing, for processing, etc. In a minute, I will go through more on this Bronto, and I will give details on that. And on top of this, we have the experimental sciences, okay, that design experiments and that have to deal with all this. Just 1 minute. I have still an hour, right? Yes, or not? It was 8:45. No, we are reaching the end of the first session. That's right. Yeah. Okay. So experimental sciences must go on top of it, and so the next session, while we go and grab a coffee and we start. Attention, the next session is on a different link. So I'm going to close this session, and then you have to connect to the other one. Okay. So we will go through more about volume and then start having a look at how to deal with this with respect to experiments. So we will meet at 4, and then I let you have a brief and then come back to the other session.